I'm Gary Ogasawara, VP of Engineering of Cloudian. Thanks for the time. So I'm going to start with a few slides, a little bit more in depth about how our system is architected and works, and then we'll jump into some of the smart topics. As Paul mentioned, we're a peer-to-peer system, so that gives us several key advantages. So one is that there's no single point of failure. We could disks fail, nodes fail, networks go down temporarily, come back up. By having each of the nodes be a peer to each other, it makes it much easier for us to manage and understand what's going on and have the system behave gracefully in the event of failures. The other thing is everything is distributed. So we're going to spray the objects that we store across the cluster, and that will inform it by certain information about user-defined location affinity. So that means like defining different data centers. So in that case, there might be a strategy that we might split, say, replicas, a certain number of replicas in one data center and a certain number of replicas in another data center. In addition to the object data, we're going to also distribute the metadata across the cluster. So we're not going to have a special node that's in charge of metadata or a set of nodes in charge of metadata. That's going to be fully distributed and treated in the same manner as our object data. And as well, the configuration. So we're going to also distribute the configuration. So by having this type of architecture, then it makes it very easy for us to be scalable, and elastic, where we could have a running system, and then without bringing any service down, we add capacity by adding a node. Then the system will automatically rebalance where things are, where things should go. In the background, it'll move some data and resume and show, this near linear scalability and performance as we add capacity.
A question for you.
Yeah.
You're showing that diagram to be peer-to-peer between every node, which obviously as you add nodes in, that's a factorial growth in terms of the communication between nodes potentially. How do you make sure that that doesn't become an issue?
Yeah, good question. So that's one of the key areas that we rely on Cassandra. So Cassandra has a very low cost, low throughput protocol, gossip protocol to understand, to do the cross-node communication. And one key is there's no global correct view of the state of the system. Each node, from its perspective, has a view on who's healthy and who's not. And it makes a decision locally in terms of well, in the most interesting case, it makes a decision about who's responding fastest to me. So I could then select that node to store my data. And this is happening times n, right, in parallel. So, yeah. And Cassandra clusters have been, we're looking at the same problem, right? But Cassandra clusters have been scaling with this gossip protocol at the level of thousands of nodes, and this continues to improve. If we double-click on one of those nodes, I want to show and talk more about what's underneath and when I say all the services are on all the nodes, what exactly are these services? So let's focus on this right half of the diagram, and we build a set of servers here, and it's fairly straightforward. So one is going to process the S3 requests from applications out there, and then one service is going to process all our admin API, which we call, and that's to do things like provision users, add new groups, add new tenants, get usage information out of the cluster, and so on. And then at the same time that we have these services processing incoming requests, we're going to actually store the data, the object data, the metadata, on the same node. So one of the differences of our system is that these services operate in application space. So what we need only is what I call commodity software. So we just run on Linux or CentOS, and you install our software, and then that allows freedom for other things that we'll get to in 2 slides to be added onto that node. So we'll go into that. So our system is smart in a lot of ways. So Paul and Vikram will have talked about it. We'll talk about some of these. I wanted to highlight these 3 things that we'll talk about today. I'll talk about the first one, metadata search and analytics. Vikram will talk about our smart support that we use internally. So, and then we won't have time, but in this session, but the third leg of this is this analytics platform. But let me go back. So, metadata search. This is a key unmet need of object storage systems, and it shouldn't be this way. So we often get the question that's very obvious. So it says, now I have all these objects stored in my system, and I want to do some simple queries against it, like this one. Like, tell me all the objects where color equals blue and size is greater than 1 megabyte. So this data is available. It could be added, and we'll show a live demo of this. The second part is smart support. So we have, for every installed system, we open up a phone home communication for them to send data back. And I'll leave this for others, but this allows us to do very interesting things for our purposes and also to help the customer. And then the third part is, we've touched on this a bit, but I should mention here is that because we run in application space, we could run side by side with things like Apache Spark, installed on Linux, running on the same hardware. This solves a lot of the problems with the data locality problems. So if you know Spark, it wants to distribute a big job into many small jobs and then stream the results back and combine them back up. One of the keys to this is data locality, right? So we don't want to send a job here that reads data from, say, another data center, right? We want to be smart and send that particular job right to the data on that node. Because we know because we manage where objects are stored, we know exactly where pieces of data are, and we could intelligently put that job right in the correct spot. And as you know, Spark has the same Hadoop layer of having a native S3 interface for in and out. So okay, let's talk about this metadata search, and I want to use the running example of a photo storage site. Right, and this is interesting because photos have a lot of metadata attached to it that's very useful, right? It has like the make and model of the phone, the location, etc. So this will allow us to answer questions like, is this a laser? What objects have make Apple and model iPhone 6s? Or what objects have size greater than 10 megabytes? Or how many objects match the keyword beach, right? So now tags, user-provided tags are very key for user-provided content. And this will allow this. Photos also have geolocation. So this allows us to do interesting things about geolocations. How many objects have geolocation in California? Or what's the average object size in my bucket? So these are the types of questions we could easily answer now. So if you remember the picture back, I'm now adding 2 new boxes to that same hardware, to that same, onto the same layer, right? And we're going to use Elasticsearch. So I'll talk about Elasticsearch, but Elasticsearch fits extremely well with our model. It's also a distributed, automatic rebalancing, auto-scaled software. So the flow is, well, I'll just leave it here. So let's see, like when I put an object, so I want to upload a photo to my object storage system. So let's see what happens, right? So I'm the client here. I'm going to get a request for an object, and then because we're a peer-to-peer system, that request can be sent to any node of the system. In this example, it's sent here. Whoops, let's go back. Here, and then that node then becomes the coordinator for this transaction only. And then that coordinator will say, okay, now let me determine where I should store replicas of that information. And then we'll send out in parallel these requests to store the data. And then at each of these data nodes, that object will be written to disk and confirmed to write. And then after that, we'll also write the metadata out to the cluster. So this is things like the object size, the access control information, and so on, encryption information. And then after both those are written, then we respond back to the client. So we haven't talked about today, but one of the keys of our system is that you could configure the consistency level of the data, right? It could be strongly consistent, or it could be eventually consistent, and you could even extend that across multiple data centers in different ways. So after that's done, then we respond back to the client. And then now we add the new part that we're here to talk about today is the ElasticSearch component, right? So now I'm going to take some of that metadata, like the photos, cameras, make and model, and I want to store that into ElasticSearch as well. So on the same transaction, then I'm going to send it back and store it into my cluster into ElasticSearch. So that's the simple idea. A little bit about Elasticsearch. As you know, we use Cassandra. We love Cassandra, and then we sort of are able to draft off it, right? So we don't need to develop everything underneath. In the same way, we want to use Elasticsearch. It's a great search engine. It provides a REST API, and important for us, it's schemaless, right? So we can't predict what fields are going to be in an object's metadata, right? So we need it to be able to accept any arbitrary key value pair, and that's an important property of Elasticsearch. And as I discussed, it's distributed, right? We could have shards of data across the cluster, and we'll do automatic routing and rebalancing. And then this will go into the query types, but it has a very powerful query language, right? So it's divided into 3 types here. One is full text. This is like a web search where you would type in a keyword, and then you'd get back a ranked set of results. So we could do the same thing here. And this is what we do for the tags, the keywords that are associated with each object. You could do a filtered. So this is like used for faceted search, right? So first, only give me the objects that are greater than 10 megabytes, or only give me the objects color equals blue. And then the third type is aggregation. So sometimes you don't want to know information about a single object, but you want to know information about a collection of objects. So you might want to know, for objects stored in this bucket, what's the average size? Or what are the min and max across this keyword that's stored? And you could make these aggregation queries and then pipeline them together in different ways to get more complex analysis and results. So going back to our photo example, so what exactly am I talking about this metadata that we'll store? But this is exactly how a request to store metadata to Elasticsearch would look like. So we would have a specific object. So in this case, it's image99.gif, and it's in a bucket, an S3 bucket called My Photos 2016. And then this LMT is the last modified time. So it has the time that the object was uploaded to the cluster, the size in bytes of that cluster, and then we're able to automatically extract metadata about the photo. And for photos, right, they have the standard metadata language called EXIF. And here's some information, right? Make, model, compression. These are keywords attached to the photo: sun, beach, cars, and then the lat long, the geolocation of it. So there's many other fields of this, but for illustrative purposes, I only list these here.
And this is an important part to think about. We're building it so this is an object storage system. We're building it so that users can define their own metadata. But there's also a lot of data we can actually automatically get from the object itself. And so what we want to build is a system that as you ingest objects, we're actually pulling out, we're grabbing useful metadata, we're automatically building the search technique. And so that you've always got that interface. You've got, of course, your S3 interface, your object interface into the data. But now you've got a set of search interfaces or query interfaces as you try to actually find relevant data across your cluster. And a lot of that index can be auto-built from us, particularly for well-defined objects like image files and video files and things that are commonly stored in object storage.
How much of a performance impact does running the queries have?
Understudy.
And how? So how would you limit that, and how would you control that?
Right. So that's understudy. One of the things to inform that, though, is you can see the amount of data is fairly tiny. But this is a real thing that we need to figure out much better.
So is ElasticSearch a standard part of your product at this point, or is it something that you add to it, or?
It's actually coming into the product. So we're actually the prototype we've already built. We're in the middle of engineering it now into the product. That's why we don't have the answers. We don't have it released yet. But towards the end of this year, we're actually expecting the release with Elasticsearch support, and I'm comfortable.
And it provides an index to the metadata as part of ingest, kind of?
Yeah, as part of ingest. As you saw, we store the object, we give back a response that says, hey, we're done with the object storing, but then we keep going in the background. We actually store now metadata into Elasticsearch so that you can then go and index it and search for it later.
So let me just sort of review how this would be done again. So first, we'd get an HTTP request, S3 request to put an object. So it would look something like this, right? So it would have certain headers, and then it would have particular fields that identify the metadata. So this is the automatic processing that can extract this from a photo, like make, model, and keywords. So this is an S3 API standard. So if you send this to Amazon S3, it will understand this and ingest it. And then you have the photo object, attached to this put request. Then we'll go ahead and store it in our cluster in a distributed manner. And then step 7, remember, is we'll then put this, our server will then put it to Elasticsearch. And then that is, again, an HTTP REST request that would look something like this. And it would have things like whatever was added, metadata was added here, it would provide it as user metadata here, in addition to some standard fields like the last modified time and the size. So once the data is in, then...
Sorry, I have a question. So if I add additional metadata fields on the original object, so they are re-indexed in some way. So after the first put, I need to add a new field to all my objects.
Yeah. So then it would, well, for each individual put, it would have to be done one by one, right now. So if you add an additional field here, say XAMZ meta special, and then with the value, then it would rewrite that value into Elasticsearch. So once the data is in, then we're going to just expose the Elasticsearch REST API to search from it. So this is just an example of how I would search for all objects where the to list the makes of the different objects, and it'll say, okay, Canon, Sony, Apple as the result. So we'll go through this in a demo. One of the awesome things about using Elasticsearch is that we get the full tool chain associated with it in the open source world. And Kibana is an open source data visualization tool that's very popular. And you could do very easy things like this, and this will we'll show more of this in the live demo. This is a live demo, so this is hitting our office up in San Mateo. And these are just two tools I'm going to demonstrate that are open source tools that come with Elasticsearch. So one of them is Sense, and Sense just provides a ability to send REST commands in this screen and then see the responses in this screen. So the other tool is Kibana. So Kibana is that data visualization tool, and what it's made for is to interact with your data, right? So it's easy to do different operations, and then you could then do analysis. So if you ask like a data analyst, what are they asked to do? They're asked to work on the data and provide interesting insights in a report. So this allows you to play back and forth, do different operations on your data to see different interesting things out of your data. So in this dashboard that I built in maybe about less than an hour, it has different built-in visualizations or widgets, right? So it has just a simple table, it has these pie charts, it has a tag cloud, it has this map where it says where were each of these photos taken. And what I want to show here is that right now it says there's 100 objects right here, and then I want to go down into the Sense and then just send some dynamic requests to populate more data, right? So I have a bunch of put statements here which will put this additional metadata into Elasticsearch. Let me go down here. Okay. Whoops. Oh, sorry, I miss. Let me just try one of these. Oh, see, someone put this string here that doesn't belong. Okay, so now back to sort of doing a bulk import. So I'm going to put these objects into the system, and this is just sending it to the server, and you can see each of these has like a make, model, keywords, and a location. Then I could go back to my visualization dashboard and refresh it, and you could see now I have 120 objects. And then this is an example of something I talked about, the aggregation operation. So this is the average size of my objects is about 3 megabytes. The median size is about 1.1 megabytes, min and max, for example. And then here's some pie charts, right? So the different make and model, you could visualize Apple, Canon, and then the different models underneath that.
And this is all being driven by Elasticsearch?
Yeah. Has different this tag cloud visualization, which it makes the different word sizes based on the frequency of the keywords. You have this nice little visualization here in terms of seeing the different data size of the object. So you could grab this, zoom in. These points will then decompose into smaller points, and so on. And then I said you could interact with your data, right? So it's hard to see, but that's a star up there. But say I only want to analyze the Apple data, right? So then immediately, then you see that instead of 120, there's 104 objects, and then the breakout of iPhone 6 and iPhone 6s. All this data is recomputed for only that subset of data. And another common one is the size. So I want to see what people are doing with, images that are 10 megabytes or greater, right? So only that set of data. So you could see there's only 6 objects in this case, and the data is different, right? So the make is different, the model is different, and so on. And then I just want to show one more thing is that if I want to, I could easily add a new visualization. So what I wanted to do is I want to add a histogram of when in weeks the objects have been last modified. So I could choose a date histogram here, last modified time, and the interval to be weekly, and then run this. And then I get this sort of graph. And then I want to save it because I want to use it in my in my dashboard. And I'll say this is an LMT histogram.
So you're doing this with respect to, you've established another, I'll call it ElasticSearch database with metadata to it. And this is being able to display and search against that separate database.
That's right.
But it's associated with the actual objects themselves?
That's right.
At time of upload or change on the objects, we're keeping all of that separate metadata database up to date. And so that's an incredibly fast database so that we can, we really want to leverage open source whenever possible because then all the tools are available.
It's not like you're going through, and I'm not even sure, with the Cassandra basic metadata object storage database. You're using this other database.
We're actually keeping another database which is optimized for search and discovery.
That's right. Okay. So then I could then store that back into my dashboard and add a new visualization. Right. So then I added my new histogram here, and I could play around with it.
Make it a little bigger.
Yeah. So let me make it a little bigger. So that's the idea. So
yeah.
So
the key thing that we're trying to do is that we think systems shouldn't just store data, particularly objects, right? Objects are described things, right? They have metadata, they have useful information. So we got to make it now incredibly easy to get that data back and to search for it and to find data. And using open source tools can get there. I think to the fact that we have to replicate the metadata, yes, that is a case in today's. So what we do is we keep up another effectively index metadata for ElasticSearch so that we can actually see, create these very, very easily. I'd love it to be one metadata source for everything, but today we can't easily do that. We did look at it architecturally on how to do that. Mm-hmm. So this is a separate metadata, but the overhead is not that huge because it's only the metadata on the objects. And so the fact that you'll have now this very flexible tool, because we don't know what customers want to do with their data, and we don't want to even guess. So what we want to do is give them a tool set and an interface that lets them go and create their dashboards, create their views, use their own data set the way they want. And that's what this allows us to do.
All right, and then I'll switch back to the original slides.
Yeah. Thank you. So any questions for Gary on this piece? Because this is one of the big extensions that we're putting into the product. And I think from our customer base, we're seeing a strong demand for it. We're seeing customers who want to they're storing so much data, they want to bring some level of analytics. And actually, surprisingly, the level of analytics they're most interested in is metadata search and discovery. Basically understanding based on the metadata what's around the place, or retention of data, or who owns what. And so it's surprising that it's not the data itself that's interesting. And I think last time around we actually showed you Hadoop analytics that you can do against our clusters. And so we certainly have that Hadoop analytics capability. But it's the metadata search, the metadata discovery is actually a huge part to it as well.